All right, so
Well, we're going to try and do these things in bite size. Haha. We're not going to try and cover too much material. We're going to bring it in small segments. That way you have a chance to absorb it. Uh, Also, it's not a bad idea, you know, a few days later to watch the segment again and just pick up on the little nuances that you may have missed out the first time. So why don't we go? Oh, by the way, this first one is a foundation, and it's all about the math. And I got to explain to you in this lesson how math works on a microprocessor. So go ahead and go to the first slide after the or next slide.
okay.
All right. When it comes to doing work, we're working with digital microprocessors. And digital, the main thing about it is you have information that's stored in a bit or whatever, and these have two states, 0 or 1, or on and off. Very simple to do, and it's very good to keep. Now, in the case of something like when you have more states for a digit, like what we usually use for math, like what we call decimal, you can have anywhere from 0 to 9 in each digit. Well, it's more likely that you might get an error where the number 4 can shift to a number 5 very easily. And a good example of this type of error is Samsung when they came out with their 840 SSD drives. After a while, they would shift because you basically had 8 states per memory cell. And sometimes what you stored in there went from like a 5 to a 4 after not rewriting the cell for about a year. And they discovered that their solid state drives were having problems. So this is one of the reasons why digital microprocessors do use digital, which is on and off for the information state. And you're going to also sit there, well, you can't do much if your answer is 0 or 1. How do you calculate 2, 3, 4, or higher numbers? Well, it's the same thing that we do with, let's see. Well, let me just continue here with what I've got on the slide. With digital, it's hard to make an error. The other thing is pretty much really easy to do math when you only have 2 possibilities per bit. Why don't we go to the next slide? Because I started to skip to that information. Okay. How do you do larger numbers than what can be held in a digit? Well, in the case of decimal or base 10, you can have 10 states per digit, 0 through 9. Binary or base 2, which is what the processor uses, only has 2 states, 0 or 1. But just, how you do the math for larger numbers is you add more digits. Let's quickly go to the next slide. Now on this slide here, I'm showing off how each of the digits hold a much larger value. Now that first box up at the top shows how you can have 1,000, 100, tens, and ones. You remember this from math in school. That's what each of the digits represent. So if you take the number 245 and you want to convert it into decimal, it is 0 times 1,000, 2 times 100, 4 times 10, and 5 times 1. That's what each of the digits represent. So you can see it comes out as 245. Now, if you want to do it in binary or base 2, you can see that each digit on the lower grid there represents a power of 2. you can have it either be 0 or 1, 0 or 2, 0 or 4 as you go across the columns until you get to 0 or 128. So if we were going to do the number 245 in binary, it would actually come out as 1, 1, 1, 1, 0, 1, 0, 1. That's an awful lot of digits to represent binary. So if we go to the next slide, there's different other base systems that you can use out there to represent the numbers. You're still doing it in binary, but you're putting the bits together. And one of the favorite ones that Motorola likes, and I have to agree with them, it's the better one, is something called hexadecimal, or base 16. Think of it as hex being 6 and decimal being 10, or 16 digits, because that's what hexadecimal is. Now, it still has what you're familiar with base 10, which is 0 through 9. And then they got really creative and came up with A, B, C, D, E, F to represent the extra numbers in hexadecimal. As you can see, computer people are really creative. And basically, A equals 10, B equals 11, C equals 12, D equals 13, E equals 14, and F, the grade that we all try to avoid in school, is 15. So to represent the number 245 in base 16 or hexadecimal, on the grid I show 256, 16, and 1 for the different digits. And there's nothing in the 256 since 245 is less than 256. So that's a 0.
Mm-hmm.
But you've got 15 for the 16 digit, and then you've got 1 for the smaller digit. So if you look at the little thing at the bottom where I show the numbers being added up, it's 15 times 16 and 5 times 1, which is 245, but comes out as F5 in hexadecimal.
Because F is the 15.
F
so that
is 15.
That number 15 under the 16 you write as F, and then the 5 is just 5. So,
and as you can see, the main reason why I bring up hexadecimal, would you rather write 2 digits, 2 numbers down, or the 8 numbers for binary?
The 8 zeros and 1s. Yeah.
And it actually makes it easier to follow.
Why not just write 245?
Because that's decimal, and the computer doesn't think decimally.
That's why I'm doing this foundation in math. The computer really speaks in binary, and I'm trying to get you to do binary or hexadecimal. That's the way the computer thinks. Now you can, in the assembler, put in decimal 10, and we'll see that as hexadecimal 0A. So there are ways to put it in easy for you to use terms, but in some cases it's better to use this hexadecimal system for the information,
right,
especially if you're pointing to a memory location. It's just easier, trust me. When I would put in pokes in BASIC, I would use the hexadecimal function for the memory location. I would not sit there and type in 65 blah 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 blah.
Yeah. Well, the number I always remember when you needed to auto boot a cartridge was exec and HC 000.
Yep.
Right. That was the number for that. But what that is, I couldn't tell you. Yeah. But I just knew that was what I typed in. I never did the math to convert it to what's that, John?
49152.
Okay, 49152. Okay. So
now I want to point one thing out here. One of the reasons that we like using hexadecimal is that it coincides, like your binary is 2 to the power of however many bits you have, and decimal is kind of in between those. You can't evenly do that in an even number of bits. It'll take more bits one way, or depending on the number, and less bits the other way. With hexadecimal, it actually matches up exactly. So every hex digit is exactly 4 bits, and represents every single representation of those 4 bits you can be from 0 to 15.
Now, there are other processors out there, PDP-11, some of the other mainframes, Intel, they like using octal. And if you remember your stuff from school, octal means 8. So instead of having it where you've got 16 numbers for the digit, you only have 0 through 7 or 8 digits. And so if you were going to write down 255, you would have to write down, oh boy, I can't even do octal that well anymore, but it would be 377.
777 or something. Yeah,
3 and 2 sevens. 377. Okay. And so it's a little longer, and you have to think about it because it doesn't, as Curtis pointed out, it doesn't break down that easily to decimal.
And it doesn't match a byte either. It's like
that too. Yeah, so it's just this hexadecimal. That's the real point here: binary and hexadecimal. Now you also notice that these numbers are what we call whole numbers. In other words, there's no decimal point. It's all integer math. And Curtis mentioned earlier, you can speed things up if you use integer math, because when you do full floating point decimal, you have a lot of calculations to do because you got to convert that into something the processor can handle, which is integer, and then convert it back as part of the calculation process.
Yeah, and you're dealing with exponents and all kinds of stuff.
And signs and so these are areas we don't want to get into at all in the beginning stages.
Agreed.
We want to keep it. Go ahead and go to the next slide.
Okay, here we go. Next slide.
Now, come on. Okay. It takes a moment to come up on my screen. Anyways, 8-bit and 16-bit numbers are used by the 6809. Now we're getting to the actual stuff of the microprocessor. That's why the 6809 is called an 8/16-bit CPU, because it can do both easily well. And as I was saying before, hexadecimal digits are represented in 4 bits, a nibble, in the binary. In other words, if you look at the line below, you can go from an 8-bit hexadecimal number can go from 00 to FF or 0 to 255. Now you understand why you never see anything like when you do a poke, it's never higher than 255. It's always some number lower than that, because that's part of the problem. Memory cell can only hold numbers from 0 to 255. Now a 16-bit hexadecimal number can go from 0 to FFFF, which is also going from 0 to 65,535 in decimal. That is its limit range. And that's also why Cocos 1 and 2 had a limit of 64K of RAM, because the 16-bit numbers primarily are used to address memory. And if you can't go over that 65,535, you can't address more than, so it wasn't worth putting in more than 64K until you start doing tricks like the Coco 3 did using memory management. Let's go to the next slide, because I actually talk a little bit about that on the next one. Okay, inside the CPU, there are 2 accumulators that are 8-bit. They're called A and B. And this is where you do most of your math. These are the things that you want to store stuff in and like that. And as I say, this is inside the CPU. And now, one trick that the 1609 does is it can take that 8-bit A and 8-bit B registers and combine them into one register called D register, which is 16 bits. They're not separate registers. The D register is the A and B being combined together. And we use the term D to refer to the 16-bit version of those two being added together.
Did that originally stand for double size, or?
Yep. It seemed to be the most logical way to put it so us programmers would remember. Now you got to remember, way back in the day when these processors were being designed, they were being designed for people that did assembly work. Because, they would go to their bosses and say, I like programming on this processor because it's nice, it does the stuff easy and like that. And so they would buy those processors to put in their equipment. Nowadays, the processors have gotten so complicated, very few people actually program in assembly on a modern processor. They'll program in C or some high-level language, and then it's compiled into the processor. But back in the day, you program assembly to get the efficiency of speed and power.
And shrink code size, too, because you could do it much more efficiently than...
Exactly. And so, basically, that was the goal. Motorola was very good at designing their processors so that if somebody had to code in assembly, they actually enjoyed it, unlike the Intel. Because every time on the Intel processor you had a way to do something, you found it only worked with particular registers or particular situations. It's a little bit like English, where you've got so many rules with so many exceptions to the rules. So where the Motorola processors were more streamlined, easier to code. If you could think about how to do something, there was a pretty good way to do it. But the main thing to think about from this slide here is we're talking about the 8-bit accumulators that do the math, the heavy lifting when it comes to arithmetic. But they can be combined together, the A and B, to make a big D 16-bit register. Next slide.
Yeah, and this was a big advantage of the 6809 over the previous things like the Z80 and the 6502 because they only had 8-bit registers, so you didn't have this nice shortcut.
Well, actually, even the 8-bit registers, the original 88 processor, there was high and low and D and E. So you had 8-bit registers that could be used as 16-bit registers because you could take the HL and the DE and kind of combine two of them together and make a 16-bit register. So they weren't quite the first people to do it, but those
No, I
were
just meant compared to the 6502 and the Z80, which were more common at the time.
Yeah, the 6502, its only 16-bit register is the program counter. Everything is 8-bit. They wanted to make the chip cheap, and they did. Anyways, now we have the 16-bit registers on the 6809. They're X, Y, U, and S, and PC. And basically, X and Y are standard pointers. The U is known as user stack, but it can be used as a regular pointer, 16-bit pointer. And of course, S is the main stack or the system stack. And they can point to any single byte of the 64K of memory. And as I said before, this is what causes the restriction of the COCO not to be able to talk to more than 64K of RAM without extra hardware like a memory management unit. And we're going to talk about that a little bit later in another segment. You can also do limited math on the X, Y, U, and S registers too. So you're not hanged out to dry where you have to do all the math in the A and B registers or the D register. You can also do some limited math in the X, Y, U, and S registers. And most of the math that you do is usually trying to figure out how to point to something. Because that's the goal, is these registers are used to point to memory.
Yeah.
Go ahead and go to the next slide.
And they're known as index registers because that's a common use, is that you have a pointer to the start of a table of data, and then you index in, I want the 5th entry or the 25th entry or whatever.
And we're definitely going to be going into a lot of that later, how we can use these pointers to create structured data blocks of information to make the coding very, very efficient. Now, on this slide here, and I know it's a little difficult to see, is how the registers are put together. Let's take a look at the very top. We have the A register and the B register. Now, the D register kind of looks like it's a different register. It is not. It's the A and B combined together into a 16-bit register. And you can see that the 0 that's on the right side represents the lowest bit. And thank you.
Mm-hmm.
And then over on the left-hand side, that's the highest bit. So, you have your choice. You can work with 8-bit numbers, and you can work with 16-bit numbers very easily. And why? You may ask yourself, why would you want to work only with 8-bit numbers? Well, if you only need an 8-bit answer, it's much faster because you don't need to do as much processing, loading of data. The data tables are smaller. But when you have, so if you can deal with from 0 to 255 as your answer, 8-bit registers are great. And that's what you use them for. And by the way, memory is only 8-bit. So if you can keep it to an 8-bit answer, things are much faster. But you've got the beauty of going to 16 bits option if you want. Now below that, you can see the different index registers, X and Y index, along with the user stack. And then you have the system stack for storing information. And we'll go through specifically what these all represent later. Because I could really confuse you by what's going on with things like the next one down, which is the direct page register. And it's basically a way to access memory in shorthand. It saves time and saves data and makes the code smaller.
It takes the MSB and instead of you having to have a 16 bits address, it takes the MSB for you.
And that's something that we definitely want to cover in a later lesson. We don't want to overdo it today.
Okay.
The program counter, well, that's the thing that points to memory of the code that you're running. And that's the key to most processors. Almost every processor has some sort of program counter because you need to know where your instruction is.
Yeah, I would say, like, the way I learned what the program counter does is it's basically kind of the same as not quite the same, but it's a similar concept as line numbers in BASIC.
Exactly.
So if you want to jump to an address, it's like jumping to a line number in BASIC.
Mm-hmm.
In this case, it's an actual location in memory, though.
Yeah, that's right.
Okay.
And here's the thing that will confuse a lot of folks. The next one, the CC register, or known as the condition code register. This is inside the processor. There's different states of the machine. There's answers to the mathematics that you're doing. Like, is the number that I just worked on 0? Was there a problem? Did I go over 255 when I did the math? So these are bits that help you understand that you had a little problem. So, and some other information about interrupts and did the entire state of the machine get saved? And these are definitely features that we will cover in a later lesson. And as I recall, that's the final slide.
Yeah, yes, it is.
Yeah. Now the question I got for the panel especially those folks that don't code that often. What did I make muddy?
This is for Steve and Ron.
Yeah, I have a question.
Okay.
So when you jump in and start programming, why wouldn't you program then in 16 bits and forget the 8-bit part and just do it all in 16 bits and it's faster and you're done?
Well, as I said while you were out, it takes more memory and more time to do 16-bit because you have to load up 2 bytes.
So it's only there for difficult parts so that it'll go faster? Or?
It's there to help you when you have to do better answers than something from 0 to 255. If you need a number that's much larger, 256 and beyond, you're definitely going to use 16-bit accumulator to do the math. Okay. And when you do that, that means that when you go to save your answer, you're saving it in 2 bytes, not 1. So your data becomes twice as large. It takes longer to access the memory because you're now having to load or save 2 bytes instead of 1.
Mm. Yeah. You have to remember the 609 is technically, as far as its data goes, it's an 8-bit CPU. So if you're storing an 8-bit value into memory, it takes 1 CPU cycle to plop whatever you're putting into memory or loading it back out. If you're doing 16 bits, it takes 2 cycles because it does 8 bits the first time, 8 bits a second time, which means any of your 16-bit stuff you're doing is actually going to take an extra CPU cycle.
So that means literally twice as long.
Right.
Yeah.
So how does that compare to another processor that doesn't have that 16-bit?
Like the 6502?
Yeah, for instance.
Well, if you're trying to do something where you're going to be pointing to memory, remember that pointer has to be 16 bits. Well, it's going to have to do a couple of loads from memory to point to that pointer. And with their 8-bit register, they just add from 0 to 255 to it, whatever's stored in that 8-bit register. And
so it's more work.
It's more work. But it makes the CPU easier to build and cheaper. And that's why Steve Wozniak used it for the Apple. They gave him one at a convention, and the chip at the time was only $40, where most of the other chips were running about $100. So that's part of the thing is savings. Motorola was very smart when they came up with this CPU. They knew that this was going to be used in smaller machines, controllers, small personal computer and like that. And this meant 8-bit. But you wanted to be able to do some heavy lifting, so you had to have 16-bit. Because that's something that the 6802 series chips, like what are used in the MC10, does not have. It's got some pointers that are 16-bit, but the arithmetic units, they're just 8-bit. You can't put them together for 16-bit.
So the 68,000 chip then will process in one cycle 16 bits each time. Like
16 or 32. It depends on which variant of the 68,000.
Yeah, the later ones were full 32-bit chips. So.
Yeah, the modern computers, they're 64-bit. And they can, but they also have very wide memory. See, that's part of the thing. The 6809 only has an 8-bit wide data bus to talk to memory. In other words, bytes have to be 8 bits. In the case of modern machines, the bytes are, 64 bits, and they actually really lay them out so they're 128 bits. So they can bring in a lot of information in one clock axis. But back in the day, when these, back in the 80s, having a 16-bit thing was very expensive, 16-bit bus. That's why Intel, when they came out with their 8086, which was a 16-bit CPU, they came out with the 8088, which got used quite a bit because its data bus was only 8 bits.
And that's what IBM chose for the original PC, because they could use 8-bit support chips instead of have to make the jump to 16.
And I programmed on some of those early IBM machines, and I could make the Cocoa run faster.
Wow.
Because part of it was accessing this information.
Bruce is asking who's running the vacuum cleaner in the background. There's definitely some background noise somewhere. I'm not sure where it's coming from.
It's me.
I think it's our friend in Europe.
That'll be my laptop overheating.
Oh, the laptop fan,
Yeah.
huh?
Yeah.
Gotcha. So the mystery has been solved.
Yeah.
And
It's
yes,
overheating.
the 6803 does not have. Oh, it does have a D register. Oh,
Yes,
okay.
it's,
a 16-bit D register.
Okay. I stand corrected.
it's got X.
Okay.
X
The 6800, 6802, which I'm more familiar with. No, they did not have a 16-bit accumulator.
yeah. The MC10 has got a D register.
Mm-hmm.
It does.
So I don't want. I know this is an introduction, and we're just trying to cover some basics of what is binary, what is a bit, what is a nibble, what is hex, the concept of the register. I understand the concept of the register, but now, without getting too technical, how do you actually access this A register and B register? Is that through assembly commands? Is it
That's
is the
exactly
A register
right.
Is it a fixed location in memory that you could effectively peek and poke into?
Well, that's the thing is, the beauty is these registers are inside the CPU. They're
inside the CPU, so it's not in memory.
It's not in memory. So they don't have to spend time accessing memory to get their information. They're already there.
Okay.
I hear somebody laughing back there.
So the A register, the B register, the combined D register, that's all stuff that you're literally looking into the CPU itself.
Right.
Same
You're
with
not
X,
looking
Y,
into memory.
U, S, C, C, D,
Okay.
all of them.
So all these things here are basically effectively, so the CPU has its own internal RAM then. These registers, this is stuff that's stored in it. All right. So I'm looking at a location inside. Literally, it's like if this was an EEPROM. You're peeling back the sticker. You're looking through the window, and you're looking inside that 6809, and you're seeing some numbers inside it. You're seeing either 8 bits for A, 8 bits for B, or 16 bits for D. So your Alpha, Bravo, Delta right there.
Mm-hmm.
You see those, and we're probably not going to cover that today. But you actually use that A and B to do math. You're also saying too, right? So whatever's in A can be used to add to something that's in B or whatever, and we won't get into that today. I'm just trying to apply what you're saying in some tangible form in my brain here. So everything you've talked about in the term of registers live in the processor, not out there in RAM.
Yeah, exactly.
When you turn the computer on, is there random stuff in all the memory?
It depends on the memory, but most cases.
Yeah.
Mm-hmm.
When I put a picture on that high screen program, the picture that comes up first before it starts doing something with bits and bytes is always the same. And there's blocks of clear area. There's a line that goes across, and then everything starts getting changed. But that screen just before everything starts working is always the same. So it's like a blank graphics representation of what's there.
All you're doing is you're showing the screen before it got initialized. However the memory came up, that's how it came up. So, but that's not part of our subject for today.
Right. Okay.
One thing that which will probably be described in the next session is that we've talked about the registers and all that are built into the CPU and what they do and all that. But the other thing we should clarify right now is that the CPU also has a language of its own, like various instructions. A lot of those numbers mean something to it. And a lot of those instructions are things like load A, LDA, or STA, store A. And there's a whole bunch of those commands. And you use the commands then to tell the CPU how to manipulate the registers and how to manipulate the memory. And that'll be something, I guess, that will be described in the next chapter.
Yep.
Yeah.
In other words, it's not just the registers and that's it. There are instructions that they represent as well. And that's assembly language. That's learning all those instructions and how to put them together. That will then allow you to play with those registers and that memory and the I/O that each machine would provide, like the video memory, the sound, all that. That's where it all starts.
So once you learn this stuff, you realize just how slow BASIC is, because BASIC is another layer doing the same stuff, but
BASIC is also general purpose. When you, like for example, the numbers in BASIC, they're floating point. And as I was saying earlier, floating point math, what we're used to when we do 37 divided by 16 on a calculator is, something, point, something. That's hard for the CPU to deal with. They have to translate it from this real number or floating point into the different elements of the integer math, do the calculations, and send it out. By the way, there's addition and subtraction in the CPU, a very limited multiply. There is no divide. So it has to go through, and remember when they said, okay, divide this number by this number and show your math, and you had that big
show your work.
Yeah, and it came down.
Unless you have a 6309.
It's that's the thing, is it's doing all that work. So every time you use a number, this is one of the reasons why BASIC is slower. It's doing all these translations to work with the number.
It's just like Ron said, it's an extra layer on top. I mean, you've got
it's a
BASIC code getting translated into machine code, and it's on BASIC's case, because it's an interpreter, it keeps redoing this over and over again, even for the same statements. And it has to do this every time, whereas if you write it in native assembly, you can skip all that stuff and just do it yourself.
And
do not think of it as like a cake that has a thin layer of icing on it. No. We're talking about layers as in a really thick piece of lasagna, and it just builds right up. There's so much stuff that's going on in BASIC because they want to be everything to everybody, and they want it to be simple for the average person. It's got lots of layers, and you have to go through them. And sometimes when you cut that lasagna, you really got to work at it.
It's important to also mention that the processor or the computer itself really doesn't know anything else but machine language. It can only really understand machine language or assembly language, let's say. It doesn't know BASIC, it doesn't know Pascal, it doesn't know Java and all that stuff. BASIC is another machine language program that is running on the computer that does all that interpreting, so that the human can talk in BASIC, the interpreter, machine language program, and the BASIC interpreter written in machine language, it then interprets the human language. So yeah, it sits sandwiched like we were just saying there. That it's a layer or it's a lasagna in between the human and the CPU. So
now, what about C? Where does C fit? C is like BASIC, right? Sort of, kind of.
No,
not quite. Yeah.
Yeah, but that's getting off topic there, Ron. Yeah. Let's stay on topic.
So I have a question.
Everything's under control. Situation normal.
So I have a question that Nick just kind of brought up. Is assembly language and machine language, are they the same thing or are they different?
Yes and no.
Yeah, they are different.
Weren't you on our After Dark where we talked about this, Grant?
I don't know if I was or not.
You were.
But it is a good
It was last Saturday.
There is a difference. So, yeah. You don't call one the other. Assembly, you write your program in something that will convert it into machine language. When you do machine language, you're actually putting down the instructions and doing all the little calculations like, okay, I've got a branch. I have to calculate where I'm branching to and write that number in. So these assembler programs do make it easier to write the assembly language, hence write the machine code that it's going to run. So you don't have to sit there and say where to, like in BASIC, you say, go to line 100, and it goes down line 100. But it figures out how far it is down to line 100. Mm-hmm. And that's part of the
assembly language is the English translation of all the machine language codes. You can either just sit there and write the numbers directly, but that is, very hard to do. I mean, I remember there were some people that used to program just in machine language, and it was just numbers. And most mortal humans can't do that. But assembly language is a way of interpreting or showing those numbers as a word, almost as a word. So where you say load A with the number 5, that would represent a string of, say, 2 numbers. One number represents the load A instruction. The second number will be the number 5. So the CPU knows it's got to load the A register with the number 5, but the human wouldn't. To make it easier for the human to understand, we use the assembly language translation of that same instruction. So it is machine language, but it's not directly machine language. It's the English translation of that machine language code.
Yeah, because if you were doing strictly machine language, you would just be dealing with numbers. Like in the case that right. Nick did of a load A with 5, that would be an 8-6 hex, which is a load A immediate instruction, and then 0-5. But then you have to memorize all these stupid codes and try to figure them out.
Some instructions take more than two bytes. There might be a string of 4 or 6 numbers to do one instruction. So it's much easier to just write the one instruction in a more English-like language, which is, I guess, the assembly language.
Yeah.
And what's a good assembler to use for a new person?
Oh, well.
I guess it depends on a few things.
Yeah, we'll be covering that later. We're going through and we're looking at what's going to be the best option as far as price and ease of use.
Okay.
Baby steps.
All right. Now, I'm somewhat fortunate in the fact that I understand binary, at least 8-bit binary. I also, to a lesser degree, understand hex. So the concept of the 0101, how that translates from binary to decimal to hex, I'm familiar with that. I through osmosis learned it using the Cocoa, even in BASIC, because things like trying to peek the screen. If you needed to put something on the screen, you needed to know what character was on the screen. I always remembered the letter A was 65 decimal. 65 was A, 66 was B. These were bytes, and we're peeking and pulling bytes off the screen. So while not knowing it at the molecular level, I understood decimal, I understood binary, and hex. And since I've been teaching like subnetting in TCP/IP, like IP version 4 is the 32-bit number that we break into 4 groups of 8 bits. I've been having to teach this for years, so I understand it, but I don't necessarily think fluently that way, but I at least understand it conceptually. So for me, that's not a new concept, but it was still good to see it put there in the forms of slides, and I don't know that everybody knows that either. So I think this is a good introduction, and I've enjoyed it so far.
Yeah,
and I'm definitely looking forward to more of these.
Yeah.
And I've always heard the word, register. You got to go to this register, but now this is the first time I've actually grasped it, and maybe it's been implied, but I didn't grasp it. But now I understand that a register is actually something internal in the CPU. So I gleaned something there that way too. So that's what this hopefully this little segment will do, is to help everybody who's not already fluent in this, latch on to a little sliver of knowledge each time.
I remember back in the day when magazines came out with unraveling the ROMs, and explain or laying out what everything was. Explain. That was kind of like important back in the day, so that people could machine language, or no?
It was more to explain how the ROMs are written in machine language. So basically those unraveled books were basically showing you the source code of the actual ROM itself for color basic. So you could actually learn how basic.
Go back and start picking certain things out, and
yeah, you'd understand how it works. You may understand how to hook into it and call it from your own programs. If you didn't want to write a floating point routine yourself, you could figure out where in the ROM to go, type thing like we were discussing earlier. But those are they're called disassemblies. They're kind of the reverse of assembly. It's taking the machine code, the raw numbers, and converting it back to the English type thing that Nick was talking about earlier. Yeah, I'll mention one other thing. Like if people have any troubles understanding how bits work, like the 1, 2, 4, 8. I found it easy when I first started. The P-Mode 4 graphics screen actually does 1 pixel per bit. So you can poke values onto the high-res screen. You can see exactly where the bits move when you poke higher values. You can see if you go 1, 2, 4, you'll see the pixel move to the left one at a time as you go up powers of 2. That helped me visualize it a lot better than me trying to just do it on paper. I don't know if that helps somebody else, but that might be something to show in a future show, just to people have a visual representation of exactly how that works.
Well, I just want to say I was able to understand this, and I want to say thanks, Steve. I think that helped helps a lot. If the rest of them are this easy, we're in good shape.
Be right back on in no time.
That's the goal. We're going to take it in small, little, easy steps that you can absorb, because I don't want to do the typical thing that David does and just blow Stevie's mind.
I think he takes a pride in doing that himself. David does.
So I think the reactions. There's been a whole sidebar conversation going on by people who I think already speak assembly, and they're speaking assembly to each other in the chat, and that's fine. But fast forwarding towards the end of that, we have Nick Marotta saying it's good to understand what computers are doing under the hood. Paul Thayer says, great intro, perfect content for the first discussion. It's sometimes hard to keep this simple, but understanding the foundation is key to the rest of programming. Paul Thayer says, it's especially good to understand what's going on under the hood when you start to simulate brain neurons like they are now, or maybe you meant stimulate there. So So yeah, no, it's good, and we've got a lot. This is what's great about this panel and this community. There's a lot of knowledge and expertise here, and this is not the first time assembly language has been discussed in the community. There's a lot of people who have been blogging. Glenn Hewlett's been blogging on assembly and optimizing assembly, and now Paul Thayer has, and so it's great. The information's out there in a lot of different forms. But for me, I like to see it and I like to hear it. So to be able to follow some bullet points and hear somebody explain it to me, it's nice sometimes to have your information spoon fed to you.
Mm-hmm.
So this is working for me so far.
Well, Steve, one thing I just wanted to add: this is not my first time doing something like this. I have taught assembly language at UCLA and at corporate places where they've had me come in and explain to their people proper techniques. And yeah, we spend about a week to 2 weeks just going over some of the initial work. And when they walk out, they go, "It's not that hard." I go, "Yeah, you just do it in baby steps."
Yeah. So it's all relative, I suppose. Good. So
what's on tap for next week?
We'll have to wait and see. Good. Everybody good with that so far?
Yep.
This concludes another episode of Coco Talk, the world's leading live talk show featuring the Tandy Color Computer. For all things Coco Talk, visit us on the web at cocotalk.live. We'd love to hear from you. Send feedback, suggestions, even segments via email to cocotalk@cocotalk.live.
Coco Talk is rocking the 8-bit world, keeping the Tandy flame alive. We may be mocked, but we'll never stop, 'cause Coco Talk is rocking the 8-bit world.
Consider supporting the show with a purchase of merchandise from our retro swag shop at 8bit256.com. If you'd like to become a patron of the show, click the Patreon link at our website at cocotalk.live.
Coco Talk is rocking the 8-bit world, keeping the Tandy flame alive. We may be mocked, but we'll never stop, 'cause Coco Talk is rocking the 8-bit world.
Coco Talk would not exist without the community, its cast, crew, and contributors. Thanks go to Curtis Boyle, David Ladd, Mark Overholzer, Grant Leedy, Bruce Moore, Nick Marentes, Ron Delvaux, Rick Adams, Jason Reichert, Richard Lorbieski, Jim Brain, Tom C., Rob Inman, Mark Bosley, Brian Joyce, Ken Reichert, David O'Connor, Brian Weasler, Terry Steggy, Nick Marotta, John Strong, and many more, especially to Steve Bjork for production suggestions and James Diffendaffer for making my head explode. Please help support the Coco community by visiting some of its various contributors. A list of resources is available at imacoconut.com. That's imacoconut.com. The Coco Talk theme song is copyright 2008 by D. Bruce Moore and Greg Sheeler. Mixed, mastered, and produced by D. Bruce Moore.